All right, let's work another indirect proof. Okay, so the theorem we're trying to prove is if n equals ab, where a and b are positive integers, so this is my premise, then a is less than or equal to square root of n, or b is less than or equal to square root of n. Okay, so the direct proof would be if p then c, assuming the premises are true, you want to show the conclusion is true. The indirect proof, you have your premise and you're negating your conclusion and you want to arrive at a contradiction. All right. Okay. So let's see, I have n equals ab, the product ab, where a and b are positive integers. So that's a premise. Okay. And let's see how we negate the conclusion. Okay, so how we negate the conclusion, we need to negate that a is less than or equal to square root of n, or b is less than or equal to square root of n. So this is an or right here. Okay, so let's actually replace it with an or. Right? So because I'm negating the whole statement, we need to use de Morgan's law to write not a less than or equal to square root of n, and not b less than square root of n. So negating the or becomes an and. Okay, so what does that mean? That it's not true that a is less than or equal to n. This means a is bigger than square root of n. And this means that b is bigger than square root of n, like this. So that's what happened when I negated my conclusion. All right, so let's see. So now we try to see if this will lead us into a contradiction. So we have n equals ab, product of a and b, where a and b are positive. Let's just write positive integers, z plus. There you go. And so n is ab. Well, I know that a is bigger than square root of n, and I know that b is bigger than square root of n. So a times b has to be bigger than square root of n times square root of n. Okay, so this leads us into n is bigger than n times n, which n squared. All right, so because there's no equality here, right, there's not even a possibility of ever of being true. So this is false, and that's a contradiction. All right, so that contradiction was arrived at because we assumed the conclusion was incorrect. Therefore, our assumption was wrong. That means the conclusion is true. All right, so that means that a has to be less than or equal to square root of n, or b has to be less than square root of n. And that concludes the proof. All right, cool. Okay, so in this next example, we're going to show a proof, an indirect proof that square root of 2 is irrational. Okay, so let's see. All right, so it's a very simple statement. Square root of 2 is irrational. So like what's our premise and what's the conclusion? So this is the conclusion. The conclusion is that square root of 2 is irrational. The premise is just basically 2 is a number, and here's square root of 2, and basically what a rational and irrational number means. So there isn't like a specified premise, it's just kind of what we know about numbers. Okay, so let's start basically with an indirect proof means that we're going to assume not C. We're going to assume the conclusion is false, all right? So what's the negation of the square root of 2 is irrational? That will be that the square root of 2 is rational. All right, so let's try to remember what rational and irrational numbers are. So a rational number is any number that can be written as a fraction, right? So an irrational number is a number that's not rational, that cannot be written as a fraction. So irrationals, we usually know things that square roots or cube roots of numbers that are not perfect squares or cubes. We know things like the number pi, the number e. Those are sort of typical irrational numbers. So we're going to use the definition of a rational, that a rational number can be written as a fraction. Okay, so we're going to write square root of 2 as a fraction, a over b. Okay, now we're going to assume a couple of things here. Again, it's sort of not really an assumption. It's sort of properties of rational numbers. So those are that b is not equal to 0, because if b is equal to 0, then that's undefined. And we're also going to assume that a over b is a reduced fraction. Okay? Because if it wasn't a reduced fraction, the first step that we're going to do in this proof is reduce it so a and b have no common factor. Okay, so a and b have no common factors. Okay, so those are good assumptions to make. All right. So what we're going to do is square both sides. Okay, so we're going to say 2 equals a squared over b squared. All right? Then I'm going to multiply both sides by b squared. So I get 2b squared equals a squared. All right, so what this tells me right here is because a squared can be written as 2 times an integer, this means, actually I should do the arrow this way. This means that a squared is even. All right, well, if a squared is even, this means that a is even. All right. And this is a theorem that can be proven. It's sort of it makes common sense, but this is a theorem that can easily be proven. You can basically say, well, if a squared is even, then a squared is 2 times an integer, and you can see that that really means that a is also even. Anyway, okay, so if a is even, then I can write a as 2 times an integer. So I'm going to write it as 2 times k, where k is an integer. And I'm going to plug this into here. All right, so now I have 2b squared equals 2k squared. So 2b squared equals 4k squared. All right, divide both sides by 2. Divide both sides by 2. And I'm going to have b squared equals 2k squared. Okay, now what does this say about b squared? So this says, because b squared is 2 times an integer, that it says b squared is even, which means b is even. Same argument as here, okay? So that means that b can be written as 2 times some other integer. That was an integer. All right. So this is a contradiction right here. Okay, so when I get to this point, this is where my contradiction is. All right. So where is the contradiction? If we look back at the beginning, I said that I can write square root of 2 as a over b because it's rational. with a over b having no common factors. All right? But what I arrived at is that a is 2 times an integer and b is 2 times an integer, and they have a common factor of 2. All right? So a and b have a common factor of 2. And that's where the contradiction is. Right? So that means my assuming the conclusion was incorrect is not valid. All right, it's not true. So that means the square root of 2 is an irrational number. All right, cool. Okay, let's look at the next example. Okay, so this is proof that if n is an integer, then n is odd, if and only if n squared is odd. All right, so this is a good one to look at because it kind of shows us kind of that information that we used in the last example. All right, so we're saying like if a squared is even, then a is even. This is basically the same proof that you would use to show that if a squared is odd, then a is odd. So kind of that these conclusions or implications that are drawing here can be explained by proving something very similar in example 6, but with odd integers. All right, so notice that this one says if and only if. All right, so this is not an implication proof. It's like a biconditional. It's an equivalence proof. So I have my premise, n is odd, if and only if n squared is odd. So my premise and my conclusion. So what this says is that I need to do 2 separate proofs. I need to go premise implies conclusion, conclusion implies premise. If you only do half of it, then it's not a complete proof. All right, so let's do this one. So this one says that if n is odd, so that's my premise. So that means I can write n as 2k plus 1. All right, then I need to show that n squared is odd. All right, so I'm taking this as true. I'm plugging it into the n squared. And I get 4k squared plus 4k plus 1. And notice that I can factor out a 2. I think we've done this one, right? Yes. And I have 2 times some integer, which is an even number, plus 1 is going to give me an odd number. All right, so n is odd. Okay, so that proved that side of the equivalence. All right, now we have to go this other way. Okay, so now we have to say, let's start with assuming n squared is odd, and then showing that n is odd. Okay, so start with n squared is odd, and show that n is odd. All right, this can be done by direct proof, but I like indirect proof better. I think it's a little simpler and cleaner to do indirect proof on this. Okay, so indirect proof says, well, assume the conclusion is wrong. So we need to negate the conclusion, which means that n is even. So we're going to say n equals 2L. All right. Then somehow that needs to contradict my other premises. So I'm going to plug this into here, and I'm going to show n squared is 2L squared, which is 4L squared, which I'm going to write as 2 times 2L squared. And because it's 2 times an integer, then that means n squared equals even. All right, But that's a contradiction because I started knowing that n squared is odd. I came to the conclusion that n squared is even, so these contradict each other. Contradiction. Don't think it's 2 words. All right. Therefore, n has to be odd. It can't be even. Right. So here's my equivalence proof going both ways. I have to go both ways to show equivalence. All right.